going. So the last thing that, okay, we got Faraday's law, and I had mentioned, okay, well, now that we've got Faraday's law under our belt, now we can go back and start talking about the circuit element. So it's kind of one of those weird ones where we already talked about qualitatively the solenoid, and then we went through and introduced Faraday's law, and now we're going to double back to the solenoid. So, so now a solenoid, again, it's just a coil of wire through which we're running a current. And so you can think of, okay, well, I've got a charge and I'm just running it around and around and around. That's my feeble attempt at trying to use Microsoft to do some sort of animation, which I should know better than for, I mean, at this point in time. But oops, there we go. For a brief moment, let's think about, hey, really what's going on at the top of the solenoid is there's a loop of wire, and what's going on at the bottom of the solenoid is that there's another loop of wire. Now granted, there's a connection between those two loops, but I just want to focus on the loop at the top and the loop at the bottom for a second. So we'll do something, okay, what's going on here? Apparently I just have too many devices hooked up. Like I've just completely lost all ability to do anything. There we go. So from a modeling standpoint, what we'll do is consider for a moment a loop of wire at the top of the solenoid where current begins to flow. So I should ask this. Let's say I'm running current in this direction as indicated. What's the direction of the magnetic field down here at this bottom loop? So if I start running the current around this loop, what's the direction of the magnetic field down here? Start that. There's all these right-hand rules. Okay, how do we get the direction of the magnetic field due to a current? Yeah, right-hand rule. What do we have to specifically do here? Point your thumb in the direction of the current, and your fingers, pretend you're grabbing the wire. Your fingers will show you the direction that the magnetic field is running. Okay. So if I'm running current around this top loop, what you end up generating is some magnetic field that is down through the center of the loop and then kind of loops around. So it's kind of like this. Let's see if I can draw that again. So it's kind of looping around and going down through the center of the loop. Grab the wire, kind of curls around the wire. Which means down here, at the location of this bottom loop, what I'm considering to be my system for a moment, up here I'm thinking the top loop as my surroundings. So down here at the bottom of the loop, as current begins to flow in the top loop, I start seeing an increase in the magnetic field, the external magnetic field, down here at the location of the bottom loop. Now, what does the bottom loop do in response to that external magnetic field? That increase in the external magnetic field. Does it like that increase? Survey says, no. It says, I don't like this increase. I will induce a field to oppose that increase. So which way is the induced field going to be pointing? Up. All right, yeah, it's an increase in the external field going down. So there will be an induced field going up. Be induced, I'll just call it I, which means that current will be running in the opposite direction. All right? To get the induced field going up, I'm running current in the opposite direction. In fact, I think I have an, yeah, there we go. Yeah, B external is going down. which means my induced current runs in the opposite direction. Now remember, I'm modeling a solenoid. So there's actually a wire connecting the top loop to the bottom loop. Which means as I start running current through the solenoid, for a brief instant, as I start, say I have an uncharged solenoid, nothing running through it, no current. As I start pushing current through that solenoid, the increased flux through the latter loops of the solenoid will try to oppose that increase in current. Right? These bottom loops see a sudden change in the magnetic field due to the top loop. Because of that sudden change, it will try to oppose that change. And you have basically the basics of how a solenoid works then, how an inductor works. Okay. So you can think of every inductor as working off of the same principle. The magnetic field generated by one part of the inductor causes a different part of the inductor to try to oppose that change. And so for a brief instant, current won't flow through that inductor, just for a very brief instant. Yeah. The induced current opposes the applied current through the inductor via the back EMF. Okay. That's just words. You already know this. This is just application of Faraday's law. The only thing I want to do is I want to quantify it. So we're using the same principles that we've been talking about for the last couple of days. Now we're at a situation where can we actually write down an equation that tells us the value, what's called the inductance. So when I crack open a computer case, I look for these little cylinders that have a silvery top. Those are the capacitors. The pumpkin roll that's, parallel plate, and then you roll it up like a pumpkin roll. And the question is, and you know that the capacitance depends on the geometric shape of the capacitor, the plate size, the plate separation. How about an inductor? Can we get an expression for the inductance based on geometric quantities, physical aspects of the loop of wire? And the survey says yes, of course we can. Let's get that derivation, let's derive it. Oh. Okay, so first question for you, thinking about this. As the number of loops increases, what happens to the inductance of the coil? I've only drawn 2, but what happens if I have more loops? What does your gut tell you? Or do you need to talk to your neighbors? Or do you have it? Increases, right? And right now I've got 1. One loop experiences this changing flux. Well, what happens if I put 2 loops in? I put a second loop down here. Well, now you're going to have the induced current on the top one, and you're going to get a second induced current, right? The more loops I put in, the more induced currents are going to add together, and then the more this whole system is going to oppose the changing flux. So as I increase the number of loops in the solenoid, the inductance of the coil will increase. There are more coils to experience that induced current due to the applied magnetic field. More coils, higher inductance. The more it will oppose a change in current. Might be a better way of saying that. How about the area of the loops? If I make the area bigger, what's your gut tell you that'll happen to the inductance? If I make the area of the bottom loops bigger. The inductance will increase, right? If I make the area bigger, the amount of magnetic field lines that pass through the coil gets increased, which means I have a higher flux, which means I'm going to have a higher back EMF, which means I'm going to have a higher inductance. Okay. Inductance doesn't want that current to flow. Okay. Yeah, so if I increase the area, I'm also going to get a higher inductance. Yeah, we're relating it to the geometric shapes, the number of loops, the area of the loops. Okay. So I think that's actually what I had here. Yeah, the area. Yeah. So, okay, let's go at it. Now, here's what I'm going to do. Let's do it this way. Let me pick out. Let's say, for example, I'm running current in the solenoid, and as we've already discussed, the magnetic field inside a solenoid is given by this mu naught big N I over L. Big N representing. Remember what big N represents? Number of loops, and L being the length of the solenoid. And so big N, I'm using number of loops and the length of the solenoid rather than the turn density. So I have an expression for mu naught, or for the magnetic field inside a solenoid. And what we will look at is, let us, for a brief moment, consider, okay, so we've got the magnetic field of the solenoid. Let us consider the flux through that last loop. So I'm thinking the flux of the entire solenoid through that one loop at the end. What should I write down? What is your expression going to be for the flux of all of the other loops, n minus 1 loops of the solenoid through that last loop? Quick, how do you calculate the flux? If I want to calculate the flux of the magnetic field, how do I calculate it? Yeah, so first of all, let's deal with the angle. Yeah, what's the angle between the area and the direction of the magnetic field for this case? 0, right? The magnetic field's that way. The area of my loop is also pointing that way. It's the same direction. Yeah, good. So 0 angle, so, okay, I've got the angle taken care of. Cosine of 0 is 1. It's always good to double check that, right? You don't want, if you're pressed for time, you don't want to have to check in your calculator what the cosine of 0 is. And so, good. Cosine of 0 is 1. And so if I want, I'm sure I have this written down in nice stuff, but if I want the flux through that loop, I just simply need to take the area of that loop and multiply by the external magnetic field. The external magnetic field being due to the rest of the solenoid. So if I want the flux through a single loop, we've identified cosine of 0. I just need the external field times the area of the loop. So I'll go ahead. Let's substitute in this external field right here. Oh, excuse me. I guess I have that out of order. Oh, where did I put it in at? Excuse me. Oh, you dirty, rotten scoundrel. My animations are out of order. I apologize. Let me do it, and I'll just write it in instead. So if I want the total flux through a single loop, okay, we put mu naught times number of loops in my solenoid times the current running through the solenoid divided by the length of the solenoid and the area of my loop. Now here's one little thing. I'll point it out to you, because if you're looking at it, you say, well, Greg, technically I shouldn't use N for the solenoid. Technically I should use N minus 1, right? Like I said, the rest of the solenoid on the last loop. So if there's N loops on the solenoid, I should technically use N minus 1, okay? I don't think I've seen a single book that ever uses N minus 1. The argument is N is really large, so if we take one less than that, it's you know, if N is 1,000,000, then I don't really care that I took one off. Okay. So if you have a solenoid that consists of 2 loops, you know, then you're really gonna have to pay attention to that. Okay. But once you get above something like 10 loops, it's not gonna make a difference. Okay. You will not have to worry about that. Anybody taking, let's see, you're taking statistics right now, aren't you? Yeah. Variance, like when you're doing the standard deviations and the variances. Yeah, I think it's the variance. You notice it's like something like, it's related to N minus 1, right? Yeah. Yeah, sometimes some formulas just have N in there. Because again, it assumes that your data points are greater than 10, and then the difference between N and N minus 1 doesn't matter. Is it with the variance that it has?
So today we talked about how like the different types of distribution, like the spread of the data.
Yeah, okay.
You use the degrees of freedom, or just like.
Yeah, it's the degrees of freedom. Yeah. So the degrees of freedom are the number of data points. Minus 1. So you'll run into this in the statistics. It's, do I use the degrees of freedom, or do I use the DOF minus 1? And the answer is, well, it depends on how many data points. If you have 100 data points, then usually you don't even worry about the minus 1. No, am I smoking? Am I blowing smoke, or am I? Have you run into this in like your statistics class?
Distribution, you don't do the N minus 1. If it's a T distribution, you do
Yeah. So sometimes you have to, yeah.
Is this function for one loop, or is it for the entire?
Well, that's a good point. Is there anything special about that one loop? This expression is for one loop. But I like the point that you've raised. Does it matter which loop I choose in the solenoid? Should there be anything special about the last loop as versus a loop halfway through? Survey says, after a certain amount of time, no. In other words, I've done this as the flux through one loop of the solenoid. What happens? How do I take into account the flux through the entire solenoid? Not just one loop, but all the loops in the solenoid. What does your gut tell you that you need to do? Multiply by N. This is the expression for the flux through a single loop of the solenoid. So if I want to do the flux through all the loops of the solenoid, I just multiply by N. Which is where my animations catch up with what I'm actually saying verbally. Right? So if I want the flux through the entire solenoid, let me just take the flux through one loop and multiply by my number of loops. Remember. So good. So now all we do is just take this and take that N and square it. Have it in there. There we go. There we go. Okay. Light patches back up. Boy, that looks a lot prettier than anything I could ever write. Let's get rid of that. I know some people say, well, when you type it out, it doesn't feel as real. Like, yeah, but when I write it, you can't read it. So, I mean, you tell me which one you want. Oops, excuse me. Yay? Oh, sorry, go ahead.
What's the end value again?
It is the number of loops in the solenoid. So capital N. You probably already know what's going to happen now. Because we've found the magnetic field, the external magnetic field. We've now found the flux of that magnetic field through a loop. Now what do you think I'm going to do? Remembering that this comes at the tail end of the discussion of Faraday's law. Sir? Now we're going to find the potential difference. Let's find out what the potential difference across the entire solenoid would be. So now I've got an expression for the flux through the solenoid. I would like to find out what's the potential drop across the solenoid. As current flows through the solenoid, by how much does the drop? Ohm's law for a solenoid instead of a resistor. Right, a resistor, Ohm's law tells us what the potential drop is if we know the current. I would like to find out what is the potential drop across a loop of wire, a solenoid, if I know what's going on with the current. So what tells us this is Ohm's law, or not Ohm's law, Faraday's law. So I just rewrote this, and I apply Faraday's law. I take the change in flux over the change in time. Now let's look at this for a second though. Mu naught, does that change in time? No. N? No. L? No. A? The only thing that can change in time is that current. The only thing that's available, everything else is a constant. Oh, and notice, I just put a delta T in there, but notice I will separate it all out. Notice I have this stuff in front, it's all constant. And oh, by the way, it only depends on the geometric arrangement of the solenoid. Right? The area of the solenoid, the length of the solenoid, the number of loops of the solenoid. Those are the geometric properties of the loop of wire. Just like when we're dealing with capacitor, the capacitance deals only with the geometric properties of the plates. Here, the inductance deals with only the geometric properties of the coil of wire. The number of coils, the length of the wire, or the length of the solenoid, the area of the solenoid. Incidentally, sorry, I don't think I have it in here. So again, you'll just have to excuse my poor handwriting. If you don't want to deal with the number of turns, if you just want the turn density instead, you could also have it as delta V equals negative mu naught little n squared, the turn density squared, times the area, and you'd still need the length of the solenoid. So I'll put L in here. So something like that. You could plug in the turn density, and you still have this delta I over delta T, how the current changes in time. Sorry, I gotta check my Wacom. It's like really lagging, so there we go. Not responding as quickly as I wanted to. Maybe I have like 6 Bluetooth devices plugged in. I don't know. If you will, this is the Ohm's law equivalent for an inductor. It relates a drop in potential to not the current, but how the current changes. This quantity right here, that depends only on the geometric the geometry of the solenoid, that is defined as the inductance. This quantity right here. And this mu naught n squared A over L, that is what we refer to as the inductance. So, yeah, say L is defined as this. Yes?
Can you explain why that L was moved to the numerator?
Oh, right here?
Yeah.
The turn density is big N divided by L. Since I have a big N squared, I want to have an L squared in the denominator, which means I just multiply by 1. So I put a little L over L so that I could write N squared, but that leaves me with this one up in. Is that okay?
Mm-hmm.
Yeah, okay, yeah. Yep. Which, again, you can see why I use the little L. I apologize, don't kill the messenger, but traditionally the variable used to refer to inductance is capital L. So usually this capital L refers to the inductance. The measure of how much a circuit element does not want to, how do I say this? It's how much the circuit element resists a changing current. So capacitance is like, oh, how much charge can the element store? This one is how much does the element resist a changing current? So a little harder conceptually to grab onto. Wicked helpful though. Give you like an application. Say, for example, it's a wonderful spring day, and you're outside and you see that line of thunderstorms rolling in, and all you think in your head is April showers bring May flowers. So this terrible thunderstorm rolls in, and you say, that's okay, I've got this wonderful physics homework that I've got to get done, I'll go inside, and I'll just work on my wonderful physics homework, which is of course on the computer. So you boot up your laptop, and realize that you spent too much time listening to Professor Robinson via Zoom, that the battery on your laptop is dead. Say, not an issue, I will plug it into the wall. And of course, the thunderstorm comes rolling in overhead, and all of a sudden, what happens? Like lightning strikes the building, or maybe a substation down the street blows up, or maybe a squirrel chews through a wire. And take your favorite. Pick your favorite. Maybe it's hail, right? I don't know, maybe it's locusts. Maybe it's a brood. Somebody will have to explain this to me at some point. Apparently we're supposed to get like an influx of cicadas. Everybody's freaking out. Right? More protein for all of us. Sustainability, just run around with your mouth open. Now, okay, so your computer's plugged in, and all of a sudden the power surges. What's a good way to protect sensitive electronics from a power surge? What's a simple, easy way to protect some sensitive electronics? Now, I use the term power surge, but really what I should say is, what is an easy way to protect your sensitive electronics from a sudden change in current? Yeah, a solenoid. Just put an inductor onto the line. The larger the change in current, the larger the back EMF. In other words, if you get a really high, fast spike in your current, your inductor will prevent that current from flowing down, from flowing through the circuit. If you get a rapid spike, it will say, whoa, 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 hold your horses, and it'll try to stop that spike from getting all the way through the circuit. It will momentarily act as if it were a brake. You ever notice this thing? Right there? If I'm not mistaken, that's the purpose of this thing. That's the inductor. So if you get a rapid spike in your line, your power supply, whether it be a surge from a lightning bolt or something else, this thing tries to stop all of that current from getting into your computer. Now, usually, in practical purposes, what happens is you still get an increase of current through the computer. The issue is that instead of getting this huge spike, it levels it out a little bit more. So it doesn't stop it from getting all the way to your computer. What it does is it tries to level it out to keep it, instead of a rapid jump, it'll clip it. So it'll be a higher current extended through a longer period of time. Because the issue is that when it spikes, it also goes back down, right? So it'll stop the rapid increase, but it will also it'll prolong the rapid decrease as well. So that's what this is supposed to do in the line. Okay. And yes, that also, I think we talked about clean power and dirty power, right? Like the orange versus the gray plugs in the walls that you see. The gray plugs have dirty power. There's a little bit more variation in the current that comes out of those plugs, whereas the orange ones, a little less variation. They're more steady. Okay. Well, one way that you can try to take care of those slight variations is put an inductor in the line. The inductor will, again, try to smooth out any rapid changes in the current. It'll filter out some of the noise, some of the dirty power. Yeah.
So is the L value really small on your inductor?
Yeah, you said, well, the L value tends to be small because this number is small, right? This is 10 to the negative 7. Yeah, you're right. Typical inductor values will be in the order of milli, 10 to the negative third. Okay. So usually, yeah, something like, the SI unit for an inductor. Of course, you could go through and figure out, okay, well, it's got, you could, meters squared per meter, okay. You could go through and actually calculate out, meters and kilograms and coulombs and everything. Usually it's called a Henry, capital H. So usually you see inductors, and you know what? I don't even know if it's a Y or an I. I assume, okay, we'll go with an I. I don't know if that's right. Okay, Google it. Come on. I. It's a Y, isn't it? No! See what you get for being creative? Okay. So it's the units of inductance are called henries. And yes, you usually end up in the millihenry range. 100 millihenries, 10 millihenries, something like that. So capacitors tend to be in the microfarad range. Inductors tend to be in the millihenry range. And again, generally the physical size of the inductor is indicative of, the inductance. What in the world? Oh. I don't know what okay. Sorry guys, give me a second. So apparently I jostled okay. So I think what the issue is, Now we're back up and running. Sorry, so I should not, apparently I shouldn't unplug my power cable and then replug it in and do all that fancy stuff. There we go. There we go. Okay, so I'll plug that back in. There we go. So usually the physical size of the inductor gives you some idea about the inductance. Because you need more, you need more loops, which means, okay, well, you've got a longer inductor, or you need a larger area. Okay, well, that's going to increase the physical size. So usually you can look at it. Now, the only other problem, well, maybe one of the other problems, if you crack open your computer case, an inductor is also going to look cylindrical. Now, usually how I can tell the difference is that a capacitor, like I said, cylindrical with a silver top. An inductor won't have that silver top on it. And usually an inductor will have the electrodes coming out of opposite sides. So a capacitor, the connections will come out on the same side. Usually an inductor, it's on opposite sides. Inductors also tend to feel really heavy. So if you put a capacitor on your hand and an inductor, you'll notice the weight difference on the inductor because literally it's a coil of wire, so it's going to be heavier. There's more material there, more metal. From a manufacturing standpoint, inductors are more expensive because you have to include more copper. Copper is more expensive than, say, aluminum. You can make capacitors out of aluminum plates. You just need a metal. Whereas an inductor, you need to actually run the current through, so you tend to go with copper, so it tends to be a little heavier. So there's all these extra considerations. But yes, that's one of the advantages, is that inductors can smooth over these rapidly changing currents. Questions so far? Let me make sure I've realized I forgot to, yeah, I'm back up on screen sharing. I'm still recording, okay. Yeah.
So is the abbreviated unit for Henry just an H if we ever?
Yes, capital H. Yeah. When in doubt, just take the first letter. Yeah. Physicists are very creative. Oh, what's a good unit for N? Newton. Okay, N. Right. Oh, what's a good unit for volt? Oh, I'll use V. What magnetic field? Oh, man, Tesla did a lot of good work. We'll just use T. Yeah, just use the first letter. I think, and you know what? The only one I can come up with where you don't use just one letter is probably Pascal. I think you do PA for that one instead of P, which I don't know why. Joule, you just use J. Yeah, I mean, man, we are really creative. So if you ever get an opportunity to name a unit, choose wisely. Right? If anything else, what is it? Georgius Sanctum, Georgius Stella should be a lesson to us all. Okay. When you discover a new planet, don't name it after King George. No, it's Sidious. It's Georgius Sidious, Sidus, I think is what it is. I don't know if I'm pronouncing that. You get one shot to name it. Choose. Because if you name it after King George, people will start calling it Ernest instead, and then you've lost your shot. You know the pattern in naming planets, right? Saturn was the father of Jupiter. So Uranus is the father of Saturn. That's why that name picked up instead of, it's like Georgius Sidious or something. No?
There's this thing that, like, Dr. Steve rule. So I think they name it Doris after my mom.
You name a what?
Doris after my mom.
Doris, yeah. The only time I think of that physicists have been creative is the cross-sectional area of particles. Oh, yeah. You guys talk cross-section? Okay, yeah. You're firing a bullet at a target, the amount that you can hit, it's called the cross-section. So if you're firing a hydrogen at an atom, you know that the cross-section is larger than the physical size of the atom. You don't have to actually hit the nucleus in order to feel the effects of the atom. So physicists, when they were doing this, they decided to they found the cross-section of an atom was something like 10 to the negative 28. And some physicists made a comment about, well, that's like hitting the broadside of a barn. So you know what the cross-section, I think it's like 10 to the negative 28 or something. You know what that cross-section is now called, that unit? Non-SI. It's called a barn, yeah.
The only like chemistry modeling experiments, what does it mean by they fire electrons or something?
Literally, you take an electron gun and you shoot electrons.
How does that work?
Usually it's you take a filament and heat it up so that the electrons boil off. Yeah. And then you accelerate it through a potential difference to get them going in the same direction. Yeah. And not to be outdone, physicists later said, I mean, since somebody said it's like hitting the broadside of a barn, so it's now known as a barn. Not to be outdone, there's also a shed and an outhouse. So that's the one time I can think of as physicists being creative with their units of labeling of units. Okay. Other questions? So you essentially have two different ways of affecting the current that runs through a circuit. Okay. One way to do that is, okay, yeah. One way to do that is that you hook up a capacitor, right? If you hook up a capacitor to a circuit, oops, there we are. Let's get some lines in here. Are you gonna let me draw? There we go. So if you hook a capacitor up to a circuit, and we'll put a resistor in there, and a switch, just for kicks. Oh, we probably need a battery too. Oh, good gravy. There we go. Make sure that that doesn't look like a capacitor. There we go. So if we hook a capacitor up to a circuit, and say it's uncharged, you know the moment that the switch shuts, there's no charge on the capacitor plate. It acts momentarily like a wire. As more and more charge gets dumped onto the capacitor plate, there is a larger and larger potential drop across the capacitor, and so the current decreases until it hits zero. The capacitor plates end up fully charged. The full drop happens across the capacitor. No drop happens across the resistor. You end up with no current. So I think I mentioned this to you. I said an uncharged capacitor initially acts like a perfect wire. And at the very end acts like a brake. When initially uncharged, it's a perfect wire. When it's fully charged, it acts like a brake in the circuit. No current flows. An inductor. So if we want to put an inductor into the circuit instead, so I'll keep my battery. Symbol for an inductor, if you are a creative physicist or electrical engineer or just a scientist in general, which you all are, if you are a creative scientist, what symbol would you use for an inductor? A little coil, just a little loop-de-loop, right? So yes, this indeed is the symbol that's used for an inductor. It's just a loop of wire, just loop-de-loop. Right, so just remind us that, hey, essentially it's like a solenoid. Not to be confused with zigzag. So that's the one thing is, you know, don't take Greg's example, because Greg is terrible at drawing apparently. But yes, if you're in a rush and you're doing an inductor, make sure it looks like a loop-de-loop. Because oftentimes if you do it fast enough, it starts looking like a zigzag, and then you'll think, oh, it's a zigzag instead of a loop-de-loop, and then you'll find yourself doing two resistors instead of an inductor and a resistor. Just be a little careful on that. And if I ever do it, you go, Greg, is that a loop-de-loop or a zigzag? So let's think for a second. if you have an uncharged inductor, in other words, no current is flowing, and you momentarily throw the switch, there's a spike in the current. And the inductor likes that spike or doesn't like that spike? Does it like the sudden rapid increase in the current through it? No, it doesn't. It says, whoa, 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 I don't like the sudden rapid increase. So for a brief moment after the switch is thrown, there's a sudden spike in the current. The inductor says, I don't like this. It acts momentarily like a break in the circuit. For a brief instant after the switch is thrown, no current flows through the circuit. It says, I don't like this, so I'm going to stop everything. Now, after that spike, right, the battery tries to maintain a constant current. After that spike, the current will gradually increase slowly. And eventually, the potential drop across the inductor will be zero. The change of the current will stop changing. The drop across the inductor will basically be zero. And the inductor acts like a break or a wire. A wire. So capacitor acts like a wire, then starts acting like a break. An inductor, exactly the opposite. It initially acts like a break, and after a long time acts like a wire. So the inductor responds to that rapid current and then acts like a wire after that. That's why, for example, stuff is getting to my computer right now. Right? Once this thing is fully charged, once the current stops changing, it just acts like another wire. I mean, it's a wire in a particular geometry, but it's just another wire in terms of circuits. Now, to remind you, for the charging capacitor, let's see, the current as a function of time was something like, let's see, a charging capacitor initially acts like a wire and ends up acting like a break. So at long times, I should get zero. Right. So I know that I should have this term e to the negative t over RC. And I just have to remind myself, okay, at long times, yes, this goes to zero. Okay. So I should have something like V over R. Again, I don't have this memorized. I just know there's an e to the negative t over RC. And then I just work through the rest of it. For the case of a charging inductor, you're still going to have that exponential behavior. It's still going to be e to the negative t. Except now we know that as time goes out to infinity, the current shouldn't drop to zero. It should drop to some constant value. So I'll give you the equations, and then we'll have to work through the rest of it. So here we'd have something like IT, and it would be still V over R. Let's see here. Rather than going to zero, what do you think I should put in here? Just out of curiosity. I'm just curious. Oops. I'll put negative t in here. As time goes up, this e to the negative t gets closer to zero. Right, so if I do 1 minus that, so at time equals 0, this is equal to 1. 1 minus 1 is 0, and so I have no current flowing. As time goes out to infinity, this drops to 0, I get 1 minus 0, and so I end up at a constant value. Which incidentally, okay, yeah, I'll leave it there for a second.
Which equation do we use for which?
Well, so this would be a charging capacitor, and this would be a charging inductor. Yeah. So this equation refers to the current going through a loop that contains the capacitor and resistor, an RC circuit. This one would be an RL circuit.
Yeah, that's charging with one minus.
I'm sorry?
Is that charging the capacitor with one minus?
The charge on the capacitor as a function of time. So if I did the charge on the capacitor as a function of time, that should give you some 1 minus behavior, because it should go up to a constant value. Let's see, what would this value be? Charge is given by the capacitance times the potential of the battery. This would be 1 minus e to the negative t over RC. And let me just make sure I have this right. The derivative, yeah, I think that's what you're thinking about. It's not the current flowing through the circuit, but rather the charge on the capacitor plate. Or similarly, the potential drop across the capacitor would be another one.
There's no value like RC in an inductor.
Purposely left out, but yes, yes. Notice that the exponential, right? The exponential for the RC circuit, we have this RC, and we defined RC as being, what did we call RC again? We called that tau. What's tau represent? We gave it the letter tau, but what is it actually? It's the time constant. It's a measure of how long does it take for the thing to charge. Larger time constants mean that it takes a longer time for the capacitor to become fully charged. Okay. Yes, so the question comes down to, is there an analogous time constant for the RL circuit? Yes. And now I have to remember what it is. So I always get it goofed up. So I'll put it down on the board and then I'll have to convince myself that this is the right way to do it. Okay? So for an RC circuit, the time constant is given by R times C. For an RL circuit, the time constant is defined as IDT. I did this here. So this equals 0. So it's right here. That means that this, I hope this is right, R over L. Which means, yes, in the exponent here, I should have some extra terms. It's not just T, it should be T times L over R. And now let me convince myself again that that's right. You got negative L I dot plus IR equals 0. So you move this over to the other side. So you get I dot equals R over L times I. And so you get an ln of I equals R over L times T. Ah! No, I think it's R over L, isn't it? This goes over, this goes here. So I have a T and R over L, which means that, so I get an E. Yep, I think I got it backwards. See, I always get these backwards. Double check, triple check. But I think this is given as L over R, not R over L.
That's what Google says.
That's what the book says? Well, we better believe the book.
No, it says Google.
That's what Google says? Oh, screw Google, I'm right. No, it should be R, excuse me. I always get that mixed up. It's L over R. And so when you put it into the exponent, you get R over L. So I took a stab at it and I got the. And the units? Henry divided by, the units of a Henry divided by an ohm. What is good? What do we call that again? What do we call tau? Time constant. What's the unit of tau? Seconds. Okay, good. So it turns out that a Henry divided by an ohm is still a second. Just like an ohm times a farad is a second. So you could break it down into base units and figure it out, but that's what you'll find out is that you get a second out of it at the end of the day. Yes.
So what is the base unit of Henry?
I'm sorry?
What's the base unit of Henry?
Oh, so you're gonna ask me for the base unit of a Henry. Okay. Well, fine, I'll try to come up with it. Let's see. We said, I'm gonna use the solenoid, but we said that the inductance of a solenoid is mu n squared A over L. So let's see. The area is meters squared, the length is meters. Shoot, now I gotta think about the units of mu naught. Sorry, give me a second here. Mu naught over 4 pi, let's see, I dl over r squared. So this tells me a Tesla must be equal to an amp times a meter divided by a meter squared times mu naught. So I get this. Okay, so mu naught has units of Tesla meters per amp. Okay, gotcha. So mu naught has Tesla meters per amp. And this whole thing is a Henry. So we get some simplification here. The meter cancels a meter. So a Henry is defined as a Tesla meter squared per amp. Okay. So now I got to get, okay, you asked for it, so we'll get it there. Let's see, Tesla. So now I got to figure out the base units of Tesla. Okay. Well, we know that a force is equal to a charge times a speed times the magnetic field. So that tells us a Newton is equal to a Coulomb meter per second times a Tesla. Which means, in more fundamental units, a Tesla is equal to a Newton second per meter Coulomb. Right? Okay, so I'll put that in. So now I've got a Newton second per meter Coulomb times meters squared, and an amp is a Coulomb per second. And you'll have to yell at me if I've made a mistake somewhere. I think we're okay. Oh, goody, goody. Oh, I get another cancellation. This meter squared cancels that meter. Well, that's nice. Okay, units of Newton. A Newton, a force, is equal to MA. So a Newton is a kilogram meter per second squared. And then I've got a second squared times a meter over a Coulomb squared. Oh, goody, goody, the seconds cancel out. So apparently a Henry is a kilogram meter squared per Coulomb squared. Now check Google. That's what I have. It's something like a kilogram meter squared per Coulomb squared. I was really hoping that those coulombs would go away, but nah, such is life. Did that answer your question? Yeah. Maybe I should have told you to figure it out. Yeah. I mean, aside from you not, like, I don't have these base units memorized, I just know the relationship, so I can rederive the base units if I need to. The hang up, you could, incidentally, I would argue you could do everything that I just did, except for maybe this mu naught. So the units of mu naught, I never remember, but I know an equation that I can use to get at. Actually, come to think of it, you could get mu naught thinking of the solenoid equation. The magnetic field of a solenoid is given by mu naught times the current times, what did I say? Mu naught times the current times the number of loops divided by L. And you could use that to get the units of mu naught. Yeah, right, Tesla, amps, and meters. So yeah, you could get, so no, I didn't do anything that you don't know how to do. You just have to know which equations to look, kind of which equations to go back to. Other questions? I gave you the charging inductor. Right, I gave you the equation for the current of a charging inductor. But you could probably take a stab at what the discharging inductor would look like. In fact, you could probably tell me. Right, if I'm discharging an inductor, what would the current look like? What should the current be after a long period of time? If I am discharging the inductor. In other words, if I am making it so there is no magnetic field stored in the solenoid, what do you think the final current would be after a long time? 0. You know, if I'm discharging the inductor, I am taking the energy that's stored in the inductor and dissipating it, running it, using it to move the current through the circuit. That doesn't happen for free. As the inductor drives the current, it loses the stored energy. The stored energy decreases. So you know that at long times it should go to 0. So just based on that, well, I know that it should have something like a T R over L. And at small times that does go to 0. So I don't need the 1 minus, I just need the exponent. And so I think it would just be something like this. Yeah. So momentarily, let's say you have a charged inductor and a resistor. You throw the switch momentarily, you know, it's V over R, and then it will exponentially decrease down to 0. So that one looks a lot like the discharging capacitor. I think the discharging capacitor, so again, this is discharging. But the discharging capacitor, if I recall, the current looks something like V over R, e to the negative T over RC. Right? As you use the stored energy in the electric field, you drive the current and it exponentially decays. So the discharging ones look very similar. Trying to remember if there's anything else. Which is also why I don't even bother to memorize. I know all these equations have that exponential in it, that e to the negative t. And then if it's an inductor, then you need the R over L. If it's the capacitor, you need the RC. So you can kind of build the rest of it out, just knowing that e to the negative t. And thinking about the behavior at time equals 0 and time equals infinity. So those are the 2 things that you can really think. I don't, like I said, I don't have these equations memorized. I just know that e to the negative t is in there. And I can kind of build out the rest of that. I don't know if you want me to show you this in Excel or not. Yeah. Yeah.
Can you explain again why it acts like a perfect wire after a long time?
So after a long time, the current stops changing. And so what's the potential drop? If the current no longer changes, what's the potential drop across the inductor? Yeah, constant, namely 0. Yeah, so if I went back, the potential drop across the inductor is given by the inductance times the change in current per unit time. So if your current ends up becoming constant, then this piece ends up going down to 0, right? If it's constant, the change in the current is 0, and so the potential drop across the inductor is 0. In other words, it's acting like a perfect wire. Yep. So you throw the switch, the current changes dramatically at the beginning, but as time progresses, the current changes less and less and less, and so the inductor acts more and more like a perfect wire. Yep, good question, yeah. Other questions? And I think that should be enough to get you moving on all the homework. Right, the charging and discharging inductors. I think that's the last piece that I was missing. Correct me if I'm wrong. Okay, we'll call that good for another day. Maybe start thinking about light here. So there's one more piece of the puzzle that I'll have to throw in. And then we can start talking about light and geometric optics and all that kind of fun stuff. So have you guys talked about light before? I mean, like frequency, wavelength, speed of light. I'm just trying to get a gauge of, okay. And you talked about? Oh, the polarized light. Yeah, I was just wondering if I need to spend time talking about wavelength and frequency, or if we can say, okay, you know what wavelength is and frequency. Okay, so maybe I'll skip over that. We'll just jump straight into light. Okay, hey, cool. Have a good Wednesday. We're halfway through.